as Michael said, we decided to switch it around a little bit, and the next several talks, the next 3 talks actually, we're going to discuss a large-scale statewide effort in California that research colleagues and ourselves are working and we're partnering with various state agencies to develop a more systematic approach to how we are developing and determining environmental flows in California. So I'm going to begin by providing a conceptual overview of how we're thinking about translating the river science that we all do into flow management practice. And I can't thank Michael enough because he absolutely set out our next set of talks beautifully. And what I'm going to do is just summarize some of the key points that he made in my first couple slides as a reminder and an intro into sort of this larger framework that the next couple talks are going to cover. Eric Stein is going to follow me, and he's going to summarize and discuss this a tiered approach that we're developing to guide the determination of environmental flows in California. And then Greg Pasternak is going to be filling in for Louise Lane, and he's going to provide an example of an approach for evaluating different flow regimes, taking into account the geomorphic settings in different places. So as Michael talked about this morning, when we think about how to translate the comprehensive and integrative science that we all do in ecohydraulics and ecohydrology, and we have to figure out how to actually put that into water management practice and policy, we often find ourselves really struggling on how do we translate that and actually make it into an implementable flow. And how do we communicate our understanding of these ecosystem processes into quantifiable measures and actions that actually are easily interpretable and implementable in these different systems. And so here's sort of a summary of a little bit what Michael already covered this morning, but what the science tells us is that it's really quite complicated. So in the realm of hydrology, we have metrics and quantifiable measures for hydrology, for hydraulics, for relationships between surface water and groundwater, and we can put numbers and values on all of those in a complex way with hundreds of metrics. On the ecological side, this lower figure down here shows a modeled food web for a stream in Baja California, and there are hundreds of species that are interacting. The green dots at the bottom represent primary producers, the red dots there represent primary consumers, and the blue dots represent things like bacteria and fungi, all of which are interacting to create hundreds of ecological processes and interactions that are happening on the ecological side. And then both of these hydrologic processes and ecologic processes then are, are interacting with geomorphic processes that are occurring at multiple scales, creating different habitat patches throughout a connected, connected river network at a large catchment scale. And then just to complicate things further, all of these hydrologic processes are interacting with each other and they're varying over time. And so how do we, it's very difficult then to take this complicated, intricate ecological system and translate that down into actual interpretable measures for a resource manager to actually implement. So, and the bottom line is what managers want is a single number. Right? There's a guy that's sitting in a dam and he opens a valve below a dam to release a flow, and all he needs to know is what's the one number of the volume that you want me to release downstream. Similarly, if I have a diversion dam like over here on the right, a manager who's operating that simply needs to know a discharge or a single number that they can divert out at a certain period of time. And so how do we then take this complexity of what we all do and the knowledge that we have and try to turn it into a number? This is an example of an environmental flow recommendation from a stream in Vermont. And you can see there's this recognition of a natural flow regime in this definition. There's a recognition that we don't want to alter it too much. But the way that we're not going to alter it is we're going to have one number, the 7Q10. The 7Q10 represents the lowest average discharge over a period of 7 days with, this is why I had to have my notes, the lowest average discharge over a period of 1 week with recurrence interval of 10 years. So one number, basically a minimum in-stream flow, just don't go below that. But that'll take into account the natural flow regime. Okay? So we want to be able to move past that. So one thing we could do, and that would help that managers come up with, is what if we give them a set of numbers and a flow schedule? So one thing we could do, and we've done this some in Northern California, is we can translate more effectively into a flow regime, like Michael talked about, a series of numbers with a timing and a number of days and a process for how you might step down those flows, which then somehow will hopefully relate back to, based on our science, the actual ecology processes. So how do we get from our complicated science to being able to do something like this that's implementable for flow managers? And this is, so what we have done in the flow ecology and our ecohydraulics and ecohydrologic communities is we developed these quantitative flow ecology and flow habitat relationships. So this is our way of trying to put numbers on these processes of intricate, complicated situations and conditions that we see, and put them into some number that can actually be converted into a discharge. So here's two examples. The upper curve is a flow ecology or species response curve. I might have some measure of species abundance or response to a change in flow on that x-axis. Or in a kind of more simplified classic design, you might have rainbow trout that has certain habitat conditions for spawning habitat, and will create some type of WUA curve or weighted usable area curve to relate habitat and flow. And this is really our only method of doing that. The problem with this, though, is that these quantitative links between flow and ecological response are typically developed for a limited set of flow metrics. When we actually go out and do our studies, we're having to pick the numbers that we want to measure in the stream to be able to relate to the stream ecology. And these metrics then often get averaged over the entire period of flow, and they're often single species focused, so they might focus on a particular life stage of a particular species. Additionally, they're static through time. They don't often take into account the variability of flow through time. And then in doing that, then they're not really particularly representative of the functions and the processes that we know that are actually happening. And then just to complicate things further, on the climate change, they don't take into account non-stationary or shifting baselines, as these things are changing over time with climate change. So we're really not capturing the ecological functionality of what we know, that complicated intricacy, when we're really only focusing on one or two flow metrics. So one solution, in terms of until we sort of figure out a larger answer to this problem, is to better translate this complexity of river science that we have into being smarter about the flow metrics that we're selecting to try to relate to our ecology. We know that there's a universe of flow metrics out there to quantify flows, right? IHA, the Indicators of Hydrologic Alteration, is 172 quantifiable metrics that you can look at in the flow regime. Richter et al. Recommended that maybe 64 of those metrics could be ecologically relevant for environmental flow assessments. 64 metrics. How do we take 64 metrics and really try to narrow that down and relate that to ecology? It's a huge challenge that our community faces. So we suggest that maybe one way to do that is to try to reduce that set down to a discrete, smaller number of flow metrics that meet the following criteria. We would want to try to pick metrics that can relate to a response and create that relationship directly between a flow metric and an ecological response in the system. And further, if we can actually pick metrics that relate to key particular life history traits, that is getting closer to this idea of trying to better quantify what a particular species needs from a flow or from a habitat and turn that into a number. It would be great if we could also find metrics that then also establish a threshold. So we have to be able to quantify what we want the flow managers to do, and we have to be able to monitor those effects. And if we can establish a threshold within those quantifiable metrics that then give us an indication, that's also very helpful. Lastly, these metrics do have to be easily quantifiable and interpretable. We're dealing with stakeholders across large systems, people from different disciplines, and so they do have to be communicatable and interpretable across different systems. And we would suggest then, one way to do that is to fit it into an ecologically based conceptual model for how we pick that. So more specifically, what I'm suggesting, and what our group is suggesting, is that we put the ecology first in determining what's important about flow. Rather than trying to quantify an aspect of flow first and determine whether or not it relates to an individual species, let's think about more broadly, what do the species need, and then figure out how to quantify that. It's a subtle difference, but I think it's an important difference in how we actually move forward. So one conceptual model, or ecological model, that we're using in California as a foundation for how we're going about trying to implement some of these ecological flows is the functional flows approach. Here the idea is from a large, just kind of step back a little bit, the large idea is to quantify key flow components that are supportive of natural disturbances, they promote the physical dynamics, so we're taking into account both the ecology and the geomorphology. They're really driving ecosystem functions, and if all of those processes can be accounted for, then we're really helping to support higher biodiversity in the system. And again, we do tend to focus on flow because flow is what's actually being regulated in the river by managers. But we can't ignore the geomorphic setting and channel floodplain dynamics that are happening. If I put a large peak flow down the LA River Canal, and I'm not actually creating the habitat that the species need, I'm not achieving the function that that species needs. So it's important to take both of those into account. And so then if we quantify those functional flow components, starting with that ecological base, perhaps then we could be getting a little bit closer to making and choosing those metrics that would be more useful for us. So, for example, if we quantify the flow components with flow characteristics, the standard off-and-off characteristics of magnitude, time, duration, frequency, and rate of change, and think about quantifying those aspects, then that helps us move forward into making sure that we're describing the aspect of the flow that we're most interested in. So what you see up here is a seasonal hydrograph. We've delineated 4 different flow components: the initiation of the wet season flows, perhaps, that might happen with a single event or a couple small events, peak magnitude flows in the wintertime, and then a spring transition or some sort of transitional flow from high flows down to low flows, and then a low summer base flow. Each of those can be quantified by looking at their magnitude, their timing, and their duration. And perhaps for the winter flow, I might consider the frequency of those winter flows occurring. So in terms of, do I want a 2-year flood or a 5% exceedance flow or a 50-year flood, for example. And if I'm thinking about the spring recession flow, I might also include the characteristic of rate of change. I want to think about how quickly I want to transition between that high flow down to that low flow. So this then allows me to think about the flow characteristics, us, I say me, but really it's us, allows us to think about the flow characteristics we want to quantify and picking metrics then that specifically put values or numbers on those flow characteristics, which then describe the flow components. And together then, this allows us to select functional flow metrics that are really grounded in an ecological concept that hopefully will get closer to achieving that relationship between what we know happens in the science and what can actually be implemented on the ground. So here's an example of one way that you might go about quantifying one of those functional flow components. So if we're thinking about the spring recession, we might go to the scientific literature and look for how many studies have actually looked at or related some characteristic, flow characteristic, or aspect of that transitional spring flow to a particular species. What's up here with the C's and the X's are examples of papers from California specifically, whereas the S might be an example of a study relating those components elsewhere, either in the Western US or elsewhere in the world. So for example, if I'm interested in rate of change, I can go, and there are several studies that have related benthic macroinvertebrates to and fish communities and riparian communities to how quickly that rate of change might need to happen. And in particular, some studies might quantify that rate of change by looking at a percent decrease in flow per day. And there's several studies actually across several of those aquatic communities that use that metric to quantify that. Another metric that quantifies rate of change for the spring recession might be to look at the average change in stage per day. This particular metric has been highly effective in looking at riparian communities. And the classic example that we often fall to is the idea of a cottonwood recruitment, and that the riparian trees need to have a certain flow where the ground bars are wet, and that water drawdown as you transition down into summer has to happen slowly enough, 2 to 3 centimeters per day, in order for the roots to follow that transition down. So both of these metrics, 3% decrease in flow per day and average change in stage per day, are quantifying the process of how we're transitioning through that flow. They're both describing the rate of change flow characteristic, and there's studies in the literature that are supporting why that metric might be a useful metric for us to use. And so then if we go to the literature, we can probably start to fill out a table like this for all of those various functional flows. So this would be an example of how we filled out this table for California, looking at the 4 functional flows that we would have identified in our system. And so what you can see here then is that if I'm filling in the boxes over here on the right for the various studies that we've been able to find, what we find is that some flow components, like the spring recession, there's a good amount of support in literature and study to help describe the types of flow metrics that would be useful to talk about that aspect, and giving us confidence that that spring recession flow is actually quite important in the ecological system for a whole variety of reasons. And that's what's outlined there in the blue box. Interestingly, when you start to fill out this table, one thing you'll notice is that I did not find a single flow study that looked at what types of summer and fall flow requirements might be needed for riparian communities. This doesn't necessarily, there's a question, does that mean that those types of flow components are not useful for the riparian community, or simply that we haven't studied them? So this was also a nice way for us to sort of look at data gaps and think about, well, there's some additional research here in terms of thinking about what might be needed by some communities at certain types of the year, and that we might have an opportunity then to better quantify those relationships. And so in summary then, we would suggest that one way of quantifying these functional flow components then provides a way to link this ecological theory, our flow, ecohydraulics, ecohydrology theory with discrete quantifiable measures of flow. So if we select those flow metrics and place them in the context of an ecological framework, it allows us to have a way to better simplify down and really start to quantify those aspects that we think are most important. And what we're really suggesting is to slightly flip our way of thinking about this by putting the ecology first, asking what pieces of the hydrograph are most important for my particular watershed and my stream community, and then quantifying that with a suite of flow metrics that are really quantifying those particular aspects. And then with that, we sort of feel like this would be a way to easily incorporate it into various environmental flow frameworks. Like Mike presented the description of the Aloha framework earlier, and this would be one way to really think about how you want to create those flow ecology relationships and assess those flow ecology relationships within that larger environmental flow framework. And so this is the approach that we're taking for the basis of an environmental flow framework that we're establishing across the state of California. And with this little bit of background then, Eric's going to be on the next talk, and he's going to talk a little bit about this tiered approach and the larger scale environmental flow framework that we're developing. And with that, I'll end and take any questions.